Hey, thanks again for checking out another episode of Triple Play. Don't forget to like, subscribe, share, and all that good stuff. And remember, we still love to have people help out and sponsor the episode. You can do so for as little as $1.99 on some of the platforms and $2.99 on others. So for $2 to $3, you can help.
Buy or guess the water.
Yeah, buy or guess the water. That's right, man.
Buy or
We
guess
could
the
use water.
Yeah.
Yeah, but help us out, and we appreciate that. The other thing we want to do is stop and thank Brookes Bible College for their sponsorship for these episodes. Brookes, if you haven't heard about them, we highly recommend you check them out. They're a solid-based Bible college here in the Midwest. They offer both biblical and counseling degrees. They're not liberal arts. They're strictly biblical, and you'll get a great education and affordable. I know I say this all the time for our repeat listeners. I'm sorry, but for those who are new, hey, if you're going into ministry and you're trying to be in missions or any of that kind of stuff, you don't want to go in with $100,000 worth of debt. And so Brookes Bible College is structured in such a way where you won't do that. You won't have to go into ministry with a bunch of debt. And so if you're pastoring a church like the average pastor in America, which is 75 to 100, you'll be able to at least not have that debt on your back and the opportunity to serve those folks. So check it out, Brookes Bible College. Their information will be in the show notes. That said, we have a great guest today. We're excited. We got Steve Grimes. Steve is from the St. Louis area, and I heard about you from Marv. Marv was talking about this guy who just did a thing with Mac on the James Webb Telescope, and I was really excited because I'm all in astronomy, and so I was reaching out to you. And what was really kind of funny was then when we got the going back and forth, that was just more of a tick for you. You went down this rabbit hole and got a bunch of information, but your real passion is more on the...
Lately, it's on origin of life relative to the creation evolution story. So, or battle.
Sounds like a movie.
There you go.
Yeah.
Origin of life.
Yeah.
But yes, it skirts the James Webb Space Telescope, and most of our NASA-based efforts now are attempting to explain how we got here. They're not shy about stating that's our purpose.
Awesome.
Well, explain where you came from, and I think that's an error, but it is resulting in some neat technology going up into space and showing us even greater glories of our Creator.
Amen. Well, tell us a little bit about yourself, where you grew up, where you went to school, the St. Louis Question, and then, give us a little bit about your testimony. How'd you come to know Christ?
Okay, well, let's see. I grew up in Ferguson, mostly. We left in the fourth grade, moved out to New Melly, Missouri, and grew up the rest of my years out there. So my high school would be Francis Howell, which at the time, we were the last class, 1977, that went through the middle school, the high school, all right there on the one campus that's right there at the beginning of a bush wildlife area. And so that's where I grew up. I'm a Lutheran. I was baptized as an infant, but and so I know that's probably strange for maybe my Baptist friends. My best man at my wedding is a Baptist pastor, or he was. He's vocational aspirations and things have changed over the years, but God remained faithful even when I became unfaithful. And so went to college at Lindenwood for a couple of years. I was a performance major on piano, and then shifted to Washington University, night school, University College at the time, and went into IT. And that's what I do today. I work as a database architect, and it's been a great career. Pays my bills, and the Lord's been faithful. So in college, I took classes on New Testament, and I knew something was wrong because they kept telling me, well, you can't trust the Bible, you can't trust this, and that kind of stirred my ire, and so it forced me to look harder at my faith. What is it I believe, and why do I believe it? And I began to, because I wasn't just going to trust the authority figure in front of me. That's probably maybe a fault, but in some times that's a good thing. And doing the study and looking closer at God's Word, I realized this is remarkable. We have something here that is beyond remarkable. This is from the hand of God. And so as the closer I got to God's Word, the stronger I got in my belief in the Word and in the truth of creation. I'm a 6-day young earth creationist. They call us YECs because we think relatively right around 6,000 years ago, God did it all. He did it in roughly 6 24-hour days. I say roughly because the Bible's not a science book, but it is our authority. That's the thing to remember. If you can show me an interpretation that is true to all the principles of hermeneutics and exegesis that describes creation slightly different than a regular 6 24-hour day, I'll listen. But you can't leave the absolute authority of God's word. That's my starting point for my thinking on all subjects. I try to make it my thinking or my orientation for all topics. And so, and that's why I'm part of the Missouri Association for Creation. I went to a talk probably in the early mid-90s. David Menton, who was the president at that time, did the talk, and his car broke down. So I had to give him a ride after the talk. So that gave me an extra hour, 90 minutes with him in the car and driving around and learning even more. And everything he said just was like lighting up my vision of how things fit together. And so became a friend with him, and started bringing my kids to the meetings every month. I still encourage people you need to get, your kids are getting bombarded from public school, from PBS, from the radio, from all the entertainment media. They are all assuming millions of years, are all assuming naturalistic causes for all the things that we see, and it's just full of holes. But how will they know that unless they're exposed to it? And so you can do things. You can have creation magazines come into your house every month. And I know I'm talking to people who go to church and Sunday school. That's fine. You're getting a couple hours a week, but you need this infused. If my kids all became atheists, they still couldn't explain this. They can't explain how the hand can do what it does. How could the mind conceive a concerto and the hand perform a concerto? What's the naturalistic explanation? Why would natural selection and random mutation lead you to a Mozart? It won't. It wouldn't, and they know that, and they've had it drilled into them. So they'd have to become a kind of atheist that still has to believe in a creator. And so and fortunately, my 4 kids have all stayed in the faith, and they all are still confessing Christians. So. That's my background, I guess.
No, I agree with what you said. I tell people all the time, I can raise my kids up in the Lord, but I think the reason why God calls the church his bride and he commands us to be involved in a local body is because having those other people come around give them those buffers so they're not just hearing it from mom and dad. Right. I always say, my kids are usually pretty good, but my let's say my oldest 2, if I bring up anything political, they'll usually roll their heads and kind of walk out the door. But if somebody at the church brings up it, might be even saying the same exact thing that I'm saying. And, usually I'm looking at things from a spiritual point of view. I'm just saying, these are things we need to be concerned about. And, they'll come in and be like, well, so-and-so agrees with you, Dad. And they listen and paid attention, and they'll be and so having those reinforcements, having other people they can talk to, not just mom and dad, that have the same belief and the same desire to see them become godly women or godly men, it to me is important. So I see exactly what you're saying. And Mac, for those listening, just so that you know, we have a Mac playlist, and this will be added to that as well. So, that's something else they can bring on their kids. We've had Helmet. We now got you. We've had Joe Brown on here, Marv on here. We did and we had the zoo where we went and visited. I think it was 10 animals, and so
we've had monkeys on here.
We've had there's a whole slew of things that they can do to be encouraged and learn about creationism and take some of this stuff and then go and learn a little bit more. Maybe that'll whet their appetite, and they'll say. Just like I did to my dad, we talk about telescopes, and we'll transition to with James Webb. But I remember going to my dad and going, I love this telescope. Isn't there more? And we started joining the St. Louis Astronomy Society. Okay. And what was great about that is we heard the other side sometimes because it was at WashU. But there were also creationists a part of that organization, and we were able to gather around with them and start hearing these other opinions. So what started whetting your appetite for the James Webb? What kind of got you going in there?
Well, it was a huge, I forget, and I don't remember the exact statistics now, that it was like 20% of NASA's budget for many years. It's close to $10 billion they spent on this thing. And so I'm not super close to all the interesting things that are going on in space. Last thing before I forget though, we live in a remarkable time when God has not left his people without resources. We have so much creation information that just has appeared in the last 20 years that compared to what it was in the 70s and 80s when I first started looking at this stuff, it's only gotten better for the creationists. There's nothing to hide from or be ashamed of. Science is breaking new frontiers in a lot of ways and a lot of places, and those frontiers are oftentimes taking us to more questions than answers. And so I love science. And so, but beyond that, it's really just a hobby. And the James Webb Space Telescope is just a remarkable piece of engineering. First and foremost, I think is if you are a naturalist or a materialist or an evolutionist, isn't it great that the planet that we are on has all the minerals and things that are necessary to build something like the James Webb Space Telescope? Because the material science alone in James Webb is amazing. And then you have the mind of man, which, just from being able to, pull bananas from trees and eat whatever evolution would have required us to survive. How do we get to the point of having a mind that lets us design something this remarkable? So my initial interest in it was just the remark. I think I caught a video on the engineering of the James Webb Space Telescope, and I think it's one of our finest achievements in engineering in history. It is broken new grounds, and we'll talk about some of the details of this. But it's just fascinating. And so that's the beginning of it. Now, when you get to the astrophysics part of it and the whole cosmology and cosmogony aspects of what is it revealing to us about the universe and solar system from the materialistic perspective, creating more questions, which is what science is doing all over the place now, especially in original life, but now in this too. And it's so it ties into those interests of mine as well.
That's awesome.
I've never actually thought about that, is that the materials on Earth alone are an oddity. Like, why wouldn't, if something came from one small little thing that held every material, when it exploded, theoretically, every piece of that material should have every piece of that material in it. Does that make sense? If I drop a breadcrumb and then explode the breadcrumb, there's breadcrumb in every single piece of breadcrumb. So why would the moon only have one type of rock? Or Yeah.
Here's another way to think about it, and it's something I need to do a little more research on. In fact, I want to go back to as soon as I retire, and I'm not quite there yet. But when I do retire, I'm probably going to go back to college and just get more physical sciences. But thinking about the periodic table, we basically understand the molecular structure of the atom, and step by step, from hydrogen to helium, to lithium, all the way up the periodic table to those elements that only exist in our science, in our laboratories or in our colliders for a moment. We can create some elements, but they're too unstable to last. In terms of the number of protons, neutrons, electrons, and the variations that are called isotopes. So you might have carbon. Carbon has multiple isotopes. So you see here, carbon-12 is one, most common. That's like 99-something%. Carbon-13, pretty rare. Carbon-14, which is unstable and decays. And so that's another isotope of carbon. We understand the periodic table. The reason I'm saying this, it's not like something's going to come from space and deliver an element that we go, oh, look at this new, make up a namium for it, and it's going to have these wonderful properties that do this or that. Material science will continue to advance because we're able to blend these atoms and elements in different ways and in new ways and create new hybrid and compounds and things. But the actual elements themselves, we understand. The reason that's important is when we look at stars, they're not made of something different because we understand the structure of the atom now and how molecules are all put together across that entire spectrum. And so now those set of rules apply not just here on the surface of this planet, which is remarkably gifted with a full set of what we need to do all this privileged planet concept. Again, we are so well positioned to discover what God has done, but that we can apply those rules to what we're observing out in space, billions of light years away. So, I find it just one more interesting aspect. And, as an evolutionist and a materialist, you just go, yep, dumb luck one more time. Get dumb luck. It's like the complete solar eclipse. The sun is 400 times bigger than the moon. The moon's 400 times closer. And dumb luck gives us the perfect vector to study the corona of the sun, which advanced our science. Thank you, Lord. But the evolutionist is stuck with, just coincidence. No other planet that we've ever observed has a moon that blocks out all of the sun except for the corona. No other planet in our solar system, no other exoplanet. It's just something we have here on this planet. So I think the evidence confirming God's creation is all around us, and the science is just revealing more of that every day.
Agree.
I agree. You know, it's interesting when you mentioned some of the technology changes and things like that. I just got done listening to a podcast literally in the past week of a major scientist. He has a research firm. And he was on, I think it was Tucker Carlson, and he spent about an hour talking about fossil fuels and how we used to think they came from dinosaurs in this prehistoric area, but that's not the case.
Well, we actually knew where it came from, and the Rothschilds changed the definition of where they came from. Did you hear about that when he told you?
Yeah.
Go ahead.
Yeah, no, you can. I was just listening, and I was sitting there. I was trying to take it all in because he was talking about that's how we now know several of these other planets that are full of them. You know, there's a moon. I think it was it Saturn's moon or Jupiter's moon? Titan, wasn't it Titan?
That sounds like Jupiter moon.
I think it's Titan that he said is full of fossil fuels. Now we know, and we could,
they're not made from. It's just decayed material, right? That's all oil is.
There are different theories for oil production. It's not, and I'm pro oil actually. Hydrocarbon is a remarkable molecule. The energy capacity of the hydrocarbon molecule and its ability for us to leverage that and release that and power things, it's been another gift from God. But there are different theories about how it forms, and I'm not all well versed on those.
Well, this guy got into it, and he said basically water is one of the key ingredients that anywhere where there's a lot of, that's why we get a lot of oil from the oceans.
Hydro.
Yeah.
Well, the Mount St. Helens, when it exploded, there was a scientist that went and studied the mountainside for 3 years or something. And the slope that collapsed had trees that fell down into a lake.
Right.
So he was able to observe these trees, and they would do this, and then they would sink, and then the root and everything would go in there, and they would start to decay. And within a matter of a couple years, that lake underneath the root systems of that level tree, whatever, all those trees started to produce oil. So within a couple of years, there was oil producing decaying material on the bottom of a lake.
Well, I think it might have been coal. But it's Steve Austin.
Okay, maybe it was coal.
And it's called there's a biomass floating log theory for the formation of coal that he actually he did his PhD work on at a secular university prior to Mount St. Helens eruption. So he was excited to go to Mount St. Helens because he could actually try out some of his ideas and observe. And it was, very remarkable what we're finding there. And it's a laboratory for creationists to explain some of the things we're...
Yeah, so he explained away the millions of years to form
You don't need millions of years. No. Not for fossils, not for coal.
And that's...
Well, now we're making, right? We make our own diamonds. We know how to make a diamond.
Well, that's what they say about the stalactites, stalagmites. You know, you go into caves. Well, I remember going into the cave in 5th, 6th grade, and they'd be like, this took thousands and maybe millions of years to form. And then as I get older, I hear stories of a guy that had a slow drip from the bottom of his barn, and there's a stalactite that only took 60 years to make.
Yeah.
Because the mineral in the water was
right. The mineral content of the soil, the hydrostatic pressure surrounding the cavity, all these things influence the formation rate of those speleotherms, and it's but what you see the secularist looks at the current rate and then they extrapolate from the current rate only. Well, when the world was covered with water, there was a lot more hydrostatic pressure on all of these cavities that weren't also filled with water, even for the decades following that.
Yeah.
So you're going to have a faster formation rate of those things.
Well, so I'm just spewing stuff at this point. Carbon-14, that's how they date things.
Organic
materials. Right. But they do that, and that can come, there's various, 10,000 year difference, or maybe it's 1,000,000 years, but they actually don't know the initial rate of decay for carbon-14. They just know within a certain period of time how a steady decay happens, but there's no initial knowledge of how fast it starts to decay.
It's carbon-14. We could have an episode just on carbon-14. I have a talk that I do on that, and it's a great, to the extent that dating methods are they what are called the basic radiometric dating methods. It's one of the better ones, I think. And the half-life, Libby, who figured it out in the 50s, he came up with 5,700 years. They've refined that, and they think it's I think they're probably pretty accurate. At least the current half-life is 5,730 years. Now, given that what you have around us in the atmosphere, and I won't do this forever, but I'll give you just a minute or two. Right now in this room, in our bodies, there's carbon. And carbon that's all around us is carbon-12. That's the vast majority of all. That's the isotope of carbon that is around us, and a little bit of carbon-13, not much. There's carbon-14 around us and inside of us, too. Roughly at the ratio of one carbon-14 atom for every trillion carbon-12 atoms. That's the starting ratio. That's what's in the air around us and in us right now. Now, if we die and we stop exchanging carbon, well, then in 5,730 years, that ratio will be 2 trillion to 1, because that one of those two carbon-14s half-life, one of them went away. So now there's one. There's still carbon-12 stable. There's 2 trillion carbon-12s to 1, and then so forth. 4 trillion to 1, 8 trillion to 1. That's how the half-life works. And so because of that, and we have these great instruments now, our dating methods with carbon-14 dating go out to about 50,000 years, 40 or 50,000 years, and then we can't count atoms any better than that. That's, the ratio is so small now between the carbon-14 and the surrounding carbon-12. Well, as a result, it's great for dating things in the last few thousand years, but as you move further and further out in time, you get looser and crazier in your dates. Mm-hmm. And the way they calibrate it recently is they'll take the records of like when this city burned, and they'll carbon date some of the wood that was in that city, and they correlate these things really within like a decade of the time. That's really good. But what they also would never expect to find is carbon-14 in anything that is 1 million years old, or 10 million years old, or 100 million. And yet what do we find? We're finding carbon-14 in diamonds, in coal, in dinosaur bones, in all these things that, per the naturalistic story, are millions and millions of years old, and yet there's carbon-14 there. It shouldn't be there. The half-life says, the rules of physics say it's going to be gone after 100,000 years. We couldn't detect it after, say, 50. No way it's even there in any form after these millions of years. And yet we're finding it in all of this stuff, anything that's organic. It's not good for minerals. We use other radiometric dating methods for that. But yeah, carbon-14 is it's a friend of creationists.
Yeah.
That's awesome. So rewinding back to James Webb, these are great. This is why we just love having a good discussion. As I told you before, we just go where the Lord leads. So this is good. So going back to James Webb, which is kind of why we had you do this presentation, you kind of got sparked. You started looking at it. Yep. What'd you start finding?
Well, first starting with the engineering. I mean, it's fascinating. It's a telescope that is designed to be in space, like the Hubble telescope. Imagine if we're going to look at space. Well, from here, we had to look through our atmosphere, which is pretty good. It's amazing. It's a gift from God that we have a clear atmosphere. It wouldn't have had to be, but it's nice that it's clear. Lets us look at the stars and think about that. But our telescopes that are, for one thing, there's light pollution on this planet. There's reflections. There's a lot of issues. There's cloudy days and all. You get something out in space, you remove all of that. So the Hubble telescope was a huge jump, and it was designed as mostly a telescope that operates in the optical spectrum of light. So it's an optical design for taking these great images and. But there's issues with that. There's a lot of cloudiness, nebula that are out in space, dust clouds, that you can't see through with an optical telescope. But with an infrared telescope, if you move the visible spectrum that telescope works in over to the infrared band of the
electromagnetic wavelength?
Yes, the wavelengths, right. I was thinking back to Maxwell and stuff. But anyway, as you move to the infrared, you get longer wavelengths that are actually longer in the wave than the size of the dust particles. It allows us to peer right through these big dust clouds to what's behind them. So it gives us even more visibility further out. Plus, it's in space, so you don't have to deal with anything with the atmosphere. So the James Webb was designed to operate in the infrared. We see infrared here as heat. I mean, that's the one way that infrared's light energy, electromagnetic spectrum is revealed to us is in the form of heat. But and so you can think of the James Webb as being super, super, super sensitive to temperature, and it is. It's so sensitive that it's been estimated that if it was sitting on the surface of this planet looking at the moon and there was no atmosphere, the James Webb Space Telescope could detect the body heat of a single bumblebee on the surface of the moon. That's how sensitive it is to temperature. So in terms of getting something out in space that can look at infrared spectrum with a degree of precision we couldn't even have dreamed of 50 years ago, we couldn't have made it 50 years ago. But material science and other things has come along. So this telescope, as part of that, that's the main goal, is to have this infrared high precision telescope. And so down to 1 photon sensitivity is what one speaker said. I've listened to a lot of lectures on it, and it's been a while, so forgive me if I get some of the finest details a little bit.
You're not an expert. You just stayed in a Holiday Inn last night, right?
Yeah, right. But anyway, so how do you put this telescope in space? Well, for one thing, it's big. It's much, has about a mirror. I think it's 6.5 meter mirror, about 21 feet. Well, the Hubble telescope is about, I think, 6 feet, something like that. It's about a fourth the size of the James Webb telescope. Hubble's great. It's been giving us great images now for decades. But we want to get this thing out there. We can't have. We have to very much control the temperature of it and the temperature of where it's looking out. So we'll never look toward the sun with James Webb. That wouldn't work. In fact, to get it out there, it has to be in a place that allows it to do this. So this gets into what's called the Lagrange points. Think of two gravitational two large masses in space, in a vacuum. They both have gravity because mass has gravity. And think one's huge, one's not so huge. There's going to be a point between those two where the amount of gravitational pull is equal, right? And it'll be a little closer to the small one because the big one's obviously got more gravity, the small one's... And all of this can be done in math. And there was a guy named Lagrange and another guy who doesn't get credit, but the two in succession, they figured this out, that there are these points when you have these major bodies that it would be very economical, very low cost to keep something in orbit or in between those two because he's being pulled equally. They're called Lagrange points. That's L1 is that point between, and that's the easiest one to understand. Well, L2 is actually on the other side of that smaller body. And then L2 is also very low energy to maintain your orbit, to maintain that spot. Because anything you put in space, we put things around our planet, but periodically they, like remember Space Lab? Periodically they're going to fall back into the planet based on a whole lot of physics that I admittedly don't understand and am not an expert at. But anyway, L2, Lagrange point 2, is about 900, it's almost 1 million miles out from Earth. Now, the moon's only 250,000 miles out from Earth, but this one's about 1 million miles out. And where it gets neat is it's in a halo orbit. Now, the halo orbit, it's not orbiting around a body, but it's orbiting like this, sort of perpendicular to the moon. And think of the moon and the Earth are sort of here doing their thing, and the sun's way over here. Well, this halo orbit, it's very important that the backside of the Webb telescope never get a shadow from the Earth or the moon. Just the shadow would alter the that would change the temperature, of the telescope. And so they have to maintain an absolute perfect temperature. And we're talking about 50, 70 degrees Kelvin for the instruments to work. Now on this back side, it's about 185 degrees Fahrenheit. On the backside that's facing the sun all the time in this halo orbit. But on the other side, it's because of the materials, this remarkable material science, we have this 5-layer heat shield, the super thin layers, and that protects it and changes on the other side. It's like 500 and something degrees Fahrenheit colder on the far side than it is on the 180. Yeah, so you got more than boiling on this side, and it's like 400 or 370 degrees below zero on the other side. It has to be that cold for it to pick up to have the sensitivity that it does of ultraviolet or infrared light out in space. So this kind of remarkable, and this all has to be folded up. These things had to unfold in space. It's way bigger than you could fit on a rocket. The heat shield is about the size of a tennis court. Well, imagine how you're going to get a tennis court in a rocket. We've all seen rockets. You've seen Apollo, and how do you get a tennis court into a rocket? Well, you got to fold it up. So not only do you have to have this big thing, you have to fold it up, get it into, and they used the largest rocket I think that we had at the time. It was launched Christmas 2001, I believe, Christmas Day. And it folds, it gets up in space. It took 6 months. They had to unfold it very carefully and then get it to its spot using as little fuel as possible. As it's designed right now, it can never be serviced. It can never be fueled. So it's going to have what it has, and then it's going to burn out like an ever-ready battery. It's just done. But it's because it was remarkably successful getting into a position. They think they may have given themselves an extra year or two or several years of life on the total life of this project. Anyway, so this is just a remarkable telescope, a million miles away from Earth in this halo orbit that's going to just start looking into space and revealing things in a degree of precision we've never even been able to get close to before.
Yeah, and we've already started seeing some stuff.
Oh, yeah. Yeah, so it's been out there. So they actually did some calibrations after they got in position and got their first images back in, I guess it was July 2002, something like that. And then fully operational. It will take years to fully digest it. These even Hubble's this way. We're still learning things from Hubble from downloads of massive amounts of data that it has been doing for the decades that it's been operating. We still haven't fully analyzed all that data because it's digitized, and then they use computers to analyze it and artificial intelligence and people and they still say, "Hey, look what we found in a Hubble image that we got 10 years ago. We never noticed this before." That's going to happen with James Webb for decades as well. Massive amounts of data are being downloaded, and the images are beautiful. If you haven't seen them, just go to
the Pillars of Life and all that.
Mm-hmm. Yeah, Pillars of Creation and the Eagle Nebula, and the just remarkable things. And then, of course, the images are great, but what's from the creationist perspective, where it really gets neat for me, is that we're seeing things that they didn't expect to see, which it's okay. It's kind of like they didn't expect to see soft tissue in dinosaur bones either, but here it is. And this is a story being repeated now with what we're seeing from the James Webb Space Telescope.
Yeah. I remember one of the very first things I learned from the James Webb, or I remember them talking about, was they could put it in almost any black spot that they thought there was nothing there. Mm-hmm. And there's literally like millions and millions of galaxies that you couldn't even see with the human eye or with the Hubble, and now we can see with the James Webb. And so the vastness of our universe and the amount of universes in space is just outstanding. It's infinite.
It is, excuse me, absolutely a testimony to the power of our Creator. Mm. Yes, what they call a deep field with Hubble, they took 1 inch of what they thought would be empty space. They knew it wouldn't be empty, but took about 1 inch little spot and looked at it for hours and got these millions. Now they're doing that. It's called the JADES part of, and I forget, the J is for the JWST, the James Webb Space Telescope. The rest of it is Advanced Digital Something Survey. I forget the acronym, but it's the JWST version of the Hubble Deep Field. And yes, it's multiple times greater in precision and in terms of what it's revealing to us.
It's pretty amazing. Yeah. And then one of the other things that I found interesting about it, and it has nothing to do with that about necessarily science, was just the fact that people could access it. You can actually apply to have access to it. Really? And I thought,
you can actually ask that you get to look at this or look at that, because not only is it looking out into deep space, it's done some of that. It's done some planets, looked at some of our planets, given us these. We can see the rings of Jupiter now that we couldn't hardly see before. But you can make requests, and they have to be, of course,
legit and presented. Yeah,
and they have to be prioritized against all the other people making requests. But it's a remarkable tool to look at space with.
Yeah.
So one of the first things I wondered, will they look for the Oort cloud? But I read a little article or two on that and said, we don't expect to be able to see the Oort cloud, which I thought, well, why not? The Oort cloud is the materialist or the secular evolutionary answer for how do we have short period or even long period, but how do we have these comets in our solar system that we know are only a few thousand years old? Well, for the young Earth creationists, it's not a problem. But for the millions of year model, these comets can't last millions of years. They're like ice cubes. They're melting. They burn up every time they go around the sun, and that's it. You get a few trips around the sun, a few being, 100 or whatever, but thousands of years. Their lifespan is measured in thousands of years, not millions, and certainly not billions. And yet we have them. Where are they coming from? So they've postulated this thing called the Oort cloud, which is a cloud full of comets that sits way, way, way out there, about 29 light days away. And once in a while, they just spits one out, and it becomes a comet that we can all see and lasts a few thousand years, and then it's gone. Because they know the comets are young and don't last that long. So, but we can't see the Oort cloud. There's been no direct observational evidence of the Oort cloud. And so I was hoping, James Webb, why don't you point it to where you think the Oort cloud is and give us that first case where you've actually had a prediction that of this sort that came true. And they said, no, we don't expect to be able to see the Oort cloud. And they have a set of reasons for that. And I can't argue with the reasons. I think it's a little bit self-serving, but I'm not an expert, so that I think they should be able to see it, because so many things don't produce light, but we can see them because when a lighted body, a star, gets behind them, we can see the impact of the light of that star based on the planet. This is how we detect a lot of exoplanets. Exoplanets that when they pass in front of their star, it changes the nature of the light we're receiving from that star, and therefore we can make some judgments about it. Sometimes there's wobbles in terms of stars because of the size of things that are going around them, or stars going around other stars. We are seeing some neat stuff in space. It's very fascinating.
I would tend not to believe that statement that they made, just because they tell us they can look at black holes.
Yes.
So like you can look at black holes, but you can't
see the Oort cloud.
Yeah. Yeah, they found a few things out about black holes too with the James Webb. So that was another area where they found information they didn't expect.
So yes, if the terms that we're going to see when you look at the findings beyond the beautiful pictures, you're going to hear the words unexpected, surprised, completely rewriting our cosmological models. There are several problems that the evolutionary unfolding of the cosmogony is I think the correct term, but a lot of people refer to it as cosmology. How did the universe, the planets, everything come to be? And there's this model. It starts with the Big Bang, has these stages that it goes through, inflation and other things, and then we finally end up with Earth and us. Well, that's a nice story, and if it's a true story, we should see some evidence of that in the earliest parts of the universe. First, if you equate distance with time, which I think you can get into trouble with doing it. So when they say something is 13 billion light years away, well, that's a measurement of distance. Now, it will often be equivocated with that meant it took 13 billion years for what we're seeing for that light to get here. That's an assumption. It's not a measure of time. It's a measure of distance. Now, it may be the right assumption. I don't know. But one of the things I say in my talk, and when you leave this planet, physics gets weird. Everybody, even creationists, how do young Earth creationists explain distant starlight? Everybody has hard things to explain when we start getting into outside of our solar system, outside of our local, what's called the local universe, which is just us and the galaxies that surround us. So you get further and further out, things get weirder and weirder in terms of what we currently understand or think about physics and how things are. I think it gets far weirder for the people trying to make a naturalistic explanation for how it came to be than it does for the creationists. But still, things get strange. So sorry to digress there, but
no, that wasn't digressing. I mean, it makes sense, right? I mean, we got gravity here, so what like if so much thrust, let's say, takes to get out of our atmosphere, but the thrust changes, right? Once you're outside the atmosphere, so you don't need as much thrust to go to a place where there's no gravity.
Right.
Yeah, and that's just a real easy, common one. But so when you talk about things get weird, I mean, anything's going to be different in outer space, right? Because you also got gravity, you've got pulls in different directions, you got all sorts of things that start to happen. And
like Voyager, it started slowing down as it left our solar system. Starts to slow down. We're not sure why. Oop.
You're good. Me. You're fine.
Just let it.
Yeah, we'll let it go. I don't understand thrust in space.
Yeah, what's the reaction? What's the pushing against? Yeah, I have trouble with that one too.
I've never heard a rational explanation. If
there's an action, there will be a equal and opposite reaction, right?
Right.
But what is it reacting against? I don't know.
Nothing. You tell me.
It's a
People
vacuum.
tell me
It's a
space is a vacuum, right? Which is void of all materials.
But in truth, there is something there. This is something Lawrence Krauss makes a big deal of. Nothing is actually something. He equivocates on the word nothing so that he can explain how everything came from nothing, which I think is baloney. It's the nice word for it. So there are some. Space is actually a vacuum, but it's not actually empty. There are, tiny little things. One of the reasons we'll never get to the speed of light and travel is because there's so much crap in space. We would hit your spaceship, would impact so much of it would destroy your spaceship. One of the theories physicists have about why we won't get to speed of light travel.
Well, there you go.
Plus, you got to stop, and if you have enough energy to get you moving that fast, the amount of energy you need to stop in this empty or
equal.
Nothing it's a problem. How do you put the brakes on? But anyway, that's not the thing.
Yeah, you got to have an object, and then it has to have gravity itself, right?
That helps.
I mean, that was one of the things that I remember Elon talking about when he was talking about his trip to Mars, so the thrust to get to Mars, ideally would be nuclear. It would shorten the distance because you're going, there's nothing you got to worry about as far as force against, so you'd go super fast.
Yeah.
I don't know about light years, but I just know it would go super fast. And then once you got there, your equal reaction would be off of the gravity in the planet of Mars. You'd have to, that would be what you would have to get
You'd use
there.
Mars, to slow you down somehow.
Yeah, I know he's put it out there. You might have to check. I'm sure he has an explanation. It was very interesting. I remember it's been years, but I remember him explaining all that just a few years ago because he was pretty upset that he didn't get the nuclear deal.
Yeah.
Maybe someday. But anyway, so back to the Webb's unexpected discoveries, a couple of them. When we classify galaxies, we see spiral galaxies. That's about 60% of all the galaxies, spiral. There's like 7 types of galaxies, but there's 3 really big types: spiral, elliptical, and irregular. Spiral and bar spiral, or just lump those into the spiral. What the theory would be, if you're going to have a star, and then you'd have to have 2 stars, 3 stars that have to cluster together, and then they would start to interact with each other gravitationally. Eventually, they might form a structure. We're not quite sure why they would structure themselves into a spiral shape, but apparently they can and do. We have all these spiral galaxies. About 60% of the galaxies we observe are spiral, but we thought their life would have to start as irregular, and then as they got more order over time, over billions of years, they'd become spiral or they'd become elliptical. So what do we find when we look through the James Webb? At the very edge of what we can see, spiral galaxies. So first they said, well, that's not spiral. This is an optical effect, and we're going to explain it away. And that's what is a lot of that's going on right now. They're trying to explain away some of these observations, and some of them they may explain away. One guy said, that's not a galaxy, that's just one star. And he had his reasons. He may be right. Maybe that's not a galaxy. But right now, I just saw a paper. It was based on JADES, which is that single deep field that the James Webb did. 737 galaxies at the very edge of the universe. By the way, if you look at the evolutionary scenario, you have the Big Bang.
That's what they think is the edge of the universe.
What they think.
Right? I mean, if we go sound out farther, we might find out just like we thought we knew how many galaxies there were.
Right. You're operating within a paradigm that says, here's how we think it all happened. And they have trouble just discarding that paradigm. We all have trouble discarding our paradigms, but there's implications to discarding the Big Bang paradigm. And one being, well, then maybe there is a creator. Can't have that. Well, so you have the Big Bang in theory, and then it's followed by these stages where you had neutrinos and all of these other subatomic elements beginning to form. And then eventually, right after the Big Bang, you have inflation. Within a trillionth of a second, what was the beginning of the Big Bang expands through this process called inflation to not quite the size it is today, but roughly the size it is today. To put it on scale, if the Earth in a trillionth of a second expanded to be the size of the universe we have today, that would be rough. That'd be ratio proportional to what inflation did. Okay, so how do physicists explain this? Well, it solves a bunch of problems with the Big Bang when you have, boom, it's all big all of a sudden. But they introduced these new subatomic particles to the standard model of physics. One was called the inflatron because they needed this subatomic particle to solve some of the problems of having enough energy to totally violate everything. It's way faster than the speed of light. This violates all kinds of stuff. And so we'd have this particle. And one of the things we looked for with the Hadron, the collider in Swiss, the CERN.
Hadron?
The Hadron Collider, yeah. We found the Higgs boson and basically not much else. We haven't found these other subatomic particles that we need to tell the Big Bang inflation story. So now I'm thinking, well, maybe inflation didn't happen at all. But so roughly, if you look at any of those models, you pull up your encyclopedias now before they start changing them, you don't even see galaxies forming till 1 billion years after the Big Bang. First stars are forming, several hundred million single stars. Well, remember, a single star has to go through a life cycle. Those early stars are type 2 stars that are going to be made up of helium, mostly helium and some hydrogen, very light elements. They have to have a whole life cycle, go through the whole stage of burning out, dying, either going into a supernova or a neutron star or something. And then that creates, at the core of those stars, you are creating the other elements, in theory, that will become the matter that is going to become part of the next generation of stars. And so you have to have these stars living, dying, to get to the heavier elements. You have to have a bunch of these stars doing that to get to galaxies. And all of that, the first galaxies are 1 billion years ago. I think I even brought a page or two from, you can just pull up Encyclopedia Britannica from 2012. You can pull up any of these. The first galaxy is about 1 billion years ago. So what are we seeing? We're seeing galaxies within 300 million, 200 million, 186 million, I think is the oldest one they found, after the Big Bang started. So we're not talking about a star. We're talking about a galaxy. And some of these galaxies are supermassive. They also found a black hole, which they didn't expect to find, because that's the end of the life of a high-density star, is to have the black hole. And that becomes the center of a galaxy. Well, we found this supermassive black hole. I've got the designation for it if you want to look it up here. It's in my notes. And this thing's way earlier than we thought. Even now, maybe black holes aren't the end of the life of a supermassive star. Maybe black holes can be formed straight from a dust cloud. They're looking for other ways to explain these things they're seeing, because it's throwing their paradigm into all kinds of fits. The Hubble constant, or what's called the Hubble tension. The Hubble constant is a number the physicists figured out about how fast is the universe expanding. And we measure it in basically 2 different ways, and we get 2 different numbers. And this is not a small problem. Something is wrong. Something is wrong with our assumptions about what's going on in the universe around. This is secular. Physicists are pointing this out. So they were hoping the James Webb Space Telescope would resolve some of the problems we're having with the Hubble constant, what's called the Hubble tension, because we can measure the constant different ways, we get different numbers. James Webb confirmed the Hubble numbers. So it didn't help at all. In fact, it refined the Hubble numbers and said your Hubble numbers are even more accurate than you thought they were. Trouble is, the Hubble numbers don't match what we get from the background radiation numbers. And we've measured this with and I've written down several of the sites. We had the Sloan Digital Sky Survey, the WMAP. We've had all these different, this isn't the first amazing telescope we've put into space. We put these other telescopes out there, and they've used these other methods to get us different measurements of the Hubble constant. And it'd be like, here's the analogy I use. I've never heard a physicist use this, so it's probably wrong. But think of a train that's a mile long, and it's traveling from Missouri to Kansas. And you measure the speed of that train, and you put some instruments in Missouri, and they're $1 billion instruments. These are the best speed cameras, the radar guns that have ever been developed. And we know they're good. We've tested them a million ways. These are $1 billion radar guns. And in Missouri, that train's going 67 miles an hour. We're 100% sure. We've got 10 different instruments. They're all telling us. In Kansas, that same train, it's a mile-long train. That same train is going 73 miles an hour with all the best $1 billion instruments we can put in Kansas. Something is wrong. Something is not adding up here. And that's part of what we're having with the Hubble tension, is we're getting these different measurements for the Hubble constant. So I don't sweat too much the whole time light problem. How can the Earth be young if this light is from billions of light years away? I don't know, but everybody's got problems as soon as they get out billions of light years away.
I think I just solved it.
I'm ready.
All right. You got a little speck of light, right? That speck of light explodes, right? Big Bang. The speck of light at the center is constantly getting light. The speed doesn't matter. The time, it's instantaneous, like you said, right? The light is there. And like you said, it's distance. there's no possible way to count how long it took for that object to there, because the light has been constant on that source since the explosion.
There are some interesting theories, and they usually have to do with the shape of the one.
That makes sense at all?
A little bit.
Yeah.
Yeah, I think to me, I liken that to like Russell Humphreys. I like his gravity well hypothesis, where if the Earth is in a gravity well, the perspective of light and of time is altered because of the shape of the universe, and in particular, our place within that shape. It's getting into physics that are beyond me, but he's got one interesting theory that's got some good points. I've never seen the math get finished. I think he's still working on that. Jason Lyle has another theory. He's another creationist, astrophysicist, who's got a different theory. And there's half a dozen theories out there for how, and so we could add yours. but they're like that. And then what has to happen is the math has to work. Mm-hmm. And these people are brilliant. Even the secular, people that aren't brilliant, like I think Dawkins is not brilliant. I think several Neil deGrasse Tyson does not impress me. But there are some brilliant atheist physicists and brilliant atheist scientists out there. Yeah, they're not necessarily the most popular ones because they're harder to listen to.
Mm-hmm.
Yeah, they get into all the crux.
Yeah.
Yeah.
Yeah. Well, all that's assuming the speed of light is constant everywhere. There's a lot of assumptions you have to make.
That's an assumption too, right?
Yeah, it really is. It's amazing. So, anything else on the James Webb? This has been a lively discussion.
Well, yeah.
Go on forever.
I'll give you a quote. This is from Isaac Newton. It's from his Mathematical Principles of Natural Philosophy. It's written in, 17th century. He's talking about the solar system, and he's figuring out the laws of gravity. And the laws of planetary motion, I think it was Kepler, that came a little later. But this is what Newton says in this, who's considered by many the greatest scientists that ever lived. This most beautiful system of the sun, planets, and comets could only proceed from the counsel and dominion of an intelligent and powerful being. That's part one. Here's part two that touches on the concept of exoplanets, which I thought is pretty cool. He didn't have a good of a telescope. And if the fixed stars are the centers of other like systems, these being formed by the likewise council must be all subject to the dominion of one. He points to the creator having set this up. And it's the problem. Neil Turek, I have a little snippet of his. He's a theoretical physicist, but he's written several books, and he's basically said, I don't believe that anymore. Here's my current thing. And he's throwing out inflatron and all these other crazy subatomic particles they're trying to introduce to explain. He said, we can't explain how it got here. This is the problem. And he's trying to now do it using just the physics of the standard model and not introduce any new particles or things they've never observed or never seen. And he said, the universe we have is really remarkably simple. It can be described with a handful of numbers. Explaining how it got that way is baffling all the greatest minds of physics. And I think there's a reason for that. And I think it's in Genesis 1. I think it's in John chapter 1. I think we have the handiwork of our Creator here.
Yeah. I always wonder what it's going to be like when we have the new heaven and new earth.
No eye can know. I have seen.
I like what Keith Green said about that, where he said, I don't know. He wasn't sure about 6 days. He says, but I do know that Jesus has been working on the new heaven and the new earth for 2,000 years. So think how much that's going to be. But not that he would need 2,000 years, but I thought it was a neat little thing to say.
I love Keith Green, so
yeah,
good stuff there.
Yep.
All right. Anything else you got for us?
That's probably the heart of it. I hope I didn't bore you too badly.
No.
I love this stuff.
You kidding me?
Well, I like the word you said, system. You think of, if a scientist ever says solar system, system, like a system,
right?
Like your brain should go to somebody had to create that system.
Right.
Yeah, absolutely.
Yeah.
Well, for those listening, we really appreciate you being here, by the way.
Yeah, thank you.
And hopefully you got a lot out of it. I know I did. I always just soak this stuff in, and I'll go back and listen to it a few times because I feel like a sponge, just constantly learning about our Creator. And as science continues to change, I'm just the one thing I keep doing is marveling at God, because I always think when you're talking about how we think we know this and then it changes, I always think, proclaiming to be wise, God proves us to be fools all the time. He says, you just think you know where the edge of the galaxy is. You just think you know. Yeah, you're not me.
I think there's stuff in the Bible about how he made everything that we maybe haven't seen yet. Like, I mean, think about God commanded the Israelites to wash their hand for cleanliness, and that's just standard science now. But it took thousands of years
For us to
for
catch.
somebody to go, wait a second, I should probably wash our hands before we deliver a baby.
Yeah. Yeah.
Yeah.
Or after gassing up a pump, right?
Yeah, that's right.
Yeah. Yeah. So,
Appreciate you coming.
Oh, my-
great.
yeah.
Yeah,
My pleasure.
very knowledgeable.
We do it.
Re-listen. I'm sure there's things that if you're listening, you missed.
absolutely. And hey, thanks again for listening in for our those who've been checking us out and those that subscribe to our podcast on whatever format you enjoy listening to it. Don't forget to help those that sponsor us. We appreciate, as we said before, Brookes Bible College, and then we got Amy McCollum with Resource One at 636-458-1798 for all your financial planning needs. Chris and CS Design does the intro, outro, the website, all that good stuff. 573-436-3717. Hopefully you're enjoying the new intro. It's a new year. And then Jeff Earhart, State Farm Agency at 314-821 Jeff, which is 5333. Check those guys out. Thanks again for listening in. Don't forget to support yourself, and we'll catch you guys next episode. And you'll catch this one also in the Mac playlist, as I said before. So make sure you guys are checking those out. Thank you so much.
Thanks, guys.
Thank you.
You're safe.